Hello, humans. My name is Professor Leach, and today we're going to talk about integrating products of powers of trig functions. In particular, we're going to be talking about the progress we've made on analyzing products of powers of trig functions. So we figured out over the weekend in the discussions, we figured out some scenarios, some more scenarios where we can use substitution when we're integrating products of powers of trig functions. Today is just about seeing how many times I could cram the phrase products of powers of trig functions into the lecture. So if you would recall, last week we talked about in the secant tangent category, if the power of secant is even, if we have an even power of secant, then the play is to substitute w equals tangent x. We'll save 2 powers of secant to be the dw, then the rest of them can be converted to tangents with the Pythagorean identity. If we have an odd power of tangent, then we can make the substitution w equals secant. We save 1 factor of secant and 1 factor of tangent to be the dw, then the remaining even number of tangents can be converted into secants with the Pythagorean identity. That's the big play, converting even powers into the other one with a Pythagorean identity. Then I set you all onto the powers of cosine and sine, and that problem has been sorted. If p is odd, that is, if we have odd cosines, then we can make a substitution of sine, because we can save 1 power of cosine to be the dw. Then we'll have an even number of cosines left that can be converted to sine. If q is odd, then we can make the substitution w equals cosine, because we'll be able to save 1 factor of sine to be the dw and convert the rest. So whichever, if we have an odd, substitute the other one. If they're both odd, then it's your choice. Although w equals sine x doesn't introduce any negatives. So let's take a look at an example of a product of powers of cosines and sines, where one of the powers is odd. So let's take a look at an example. Let's say we have cosine to the 4th x times sine to the 5th x to x. So we have a product of 4 cosines and 5 sines. Since the power of sine is odd, that's where I'm going to get my 1 factor of dw. So the cosine sine one is a little bit easier because our dw's are always just 1 factor. In secants and tangents, our dw was made up of 2 factors. Derivative of tangent is secant squared. The derivative of secant is secant tangent. But the derivative of sine is cosine. The derivative of cosine is negative sine. So it's a little bit smaller problem to work with. Since the power of sine is odd, since we have an odd power of sine, we'll make w cosine. Since we have an odd power of sine, since we have an odd power of sine, that's where we're going to get our dw. So we're going to substitute w equals cosine x. Since w is going to be cosine x, dw will be negative sine x dx. And so minus dw is sine x dx. So this is why the odd one is where we get our dw. I'll switch green pens. The odd one is where we get our dw. So that'll leave 4 sines behind when I set one of them aside to be the dw, and I can convert the rest of the signs to cosines. So once I make these, so I'm going to read this problem as the integral of cosine to the fourth. Cosine is going to be the w, so I'm going to write that. Cosine of x to the cosine fourth x is going to be the w. I'm going to separate out one factor of sine to be the dw. And then the remaining four factors of sine, I'll be able to write as cosine. So it's a sine to the fourth left over. And then the dx is going to go with the sine x to make a dw. So in this case, sine to the fourth x, we're going to read that as sine squared x squared. And we can replace the sine squared with 1 minus cosine squared. And cosine is going to be the w, so that's how the substitution breaks down. We're always looking to have an even power of the one that we're not substituting. And we're going to use Pythagorean identities to convert those. So my integral becomes cosine to the fourth is going to be a w to the fourth. So cosine is w to the fourth. We have 1 minus cosine squared squared. So I have 1 minus w squared squared. And then the sine x dx all becomes a minus 1 times dw, because sine x dx is minus dw. And now we've got an integral in w. We can just multiply all this stuff out and write it as powers of w, because if we can write powers of the variable, then we should write powers of the variable. 1 minus w squared, we can simplify that. That's going to be a 1 minus 2w squared plus w to the fourth. So all this is going to become the integral. If I multiply by a minus w to the fourth, I'll have a minus w to the fourth plus 2w to the sixth minus w to the eighth dw. Now I've got just powers of w, which is what we wanted in the first place. So we integrate. So it's a minus 1/5 w to the fifth plus 2/7 w to the seventh minus 1/9 w to the ninth plus c. And then the final thing that we have to do is replace our w's with cosine x. So finally, we have a minus 1/5 cosine of the fifth x plus 2/7 cosine of the seventh x minus 1/9 cosine of the ninth x plus c. I suppose in this case, we could factor out the fraction and a negative and 5 powers of cosine, but it would still leave us with a polynomial in terms of cosine. So there's not really a lot of percentage. I'd still have to write 3 powers of cosine. I'd have, even if I had a cosine of the fifth on the outside of some parentheses, I'd have a 1 plus a cosine squared plus a cosine to the fourth. So I'm still doing a lot of writing of cosine. So we're just going to leave it that way. Any questions? All right. So we've got a plan for lots of cases. For cosines and sines, we need one of the powers to be odd, and then we substitute the other one. In the case of secants and tangents, with an even power of secant, we can make the substitution W equals tangent. With an odd power of tangent, we can make the substitution W equals secant. Also, with an odd power of tangent, we can convert the tangents and secants into sines and cosines, and we'll have an odd power of sines. So one thing that we should observe is that an odd power of tangents also means an odd power of sines. So we should make a note of that. An odd power of tangent, since tangent is sine over cosine, an odd power of tangent can be converted to an odd power of sines. So note, an odd power of tangent can be written as an odd power of sines. An odd power of tangent can be written as an odd power of sine. So we can view the integral of secant to the px tangent to the qx dx as secant can be 1 over cosine to the negative p, or 1 over cosine of the p, and then tangent of q can be sine to the q over cosine of the q. So I could view this as sine to the q over of x over cosine to the p plus q of x dx. And if q is odd, I can make the substitution W equals cosine. So in this case, if q is odd, now we're in the sine and cosine analysis. If q is odd, we can make the substitution W equals cosine. So this leaves us with just 2 non-substitution cases. Any questions on this converting bit? Because I just kind of like threw that in there and said, hey, we can take the secants and tangents.
Cosine p plus q is just because they're the common denominator, right?
No, not a common denominator. It's 1 over cosine of the p times 1 over cosine of the q. We're multiplying things with the same base, so we add the exponents.
Got it. Wrong terminology.
Yeah. So let's look at our 2 cases that are not substitution problems, because that's what we have to deal with now. So there are 2 cases that are not substitution. Even powers of cosine even powers of cosine and even powers of sine. Oops. So one case that's not substitution is when we have even powers of cosine and even powers of sine. We're going to summarize this case by calling this even powers of cosine for future reasons. I'm just going to leave it this way. Nope, I'm going to call it even powers of cosine. I always do, so. So we can simplify this case to even powers of cosine. If you have an even power of sine, you can convert those to cosine. And really what we're going after is even powers of cosine. We need a solution for that. Case number 2 is odd powers of secants paired with even powers of tangents. Neither of our secant and tangent substitutions will work. So odd powers of secant with even powers of tangent. So case 2 that's not a substitution is odd powers of secant with even powers of tangent. We're going to simplify this one as well. Odd powers of secant with even powers of tangent can be simplified to odd powers of secant on their own. So we're going to, just like we're going to simplify even powers of cosine and even powers of sine to just even powers of cosine. If we can deal with even powers of cosine, then the even powers of sine will just become even powers of cosine. If we have odd powers of secant and even powers of tangent, we're going to write that as odd powers of secant. So what I mean is, if I have the integral of cosine squared x times sine to the 4th x dx, even powers of an even power of cosine and an even power of sine, I'm going to rewrite the signs in terms of cosine. I'm going to simplify this to just even powers of cosine. So we're going to replace sine to the 4th with sine squared squared. So I'm going to rewrite this as sine squared x all squared. And this will become cosine squared x times 1 minus cosine squared all squared. 1 minus cosine squared can be simplified as 1 minus 2 cosine squared x plus cosine of the 4th x. And then I can multiply by the cosine. So we have the integral of cosine squared x minus 2 cosine of the 4th x plus cosine of the 6th x dx. So if we can deal with even powers of cosine, then if there are also even powers of sine, we can take care of those as well. So the core problem we need to solve is even powers of cosine on their own. The core issue is now even powers of cosine. Similarly, odd powers of secant and tangent. If we have an odd power of secant, the same thing is we're going to be able to simplify that to just secants. So if I have an odd power of secant and an even power of tangent, I can imagine the tangent, I'm just going to replace tangent squared. I dropped it down one. It's getting lazy, I guess. So secant cubed x, the tangent squared will replace with 1 minus, tangent is 1 minus secant squared, secant squared minus 1. Tangent squared is secant squared x minus 1. And if I had started off with a higher power of tangent, so if it was tangent to the 4th, then I would just read that as tangent squared squared. And then I would just square my secant squared minus 1. Then I'll multiply this, and the core issue will become odd powers of secants without tangents, just like the core issue with the cosine was even powers of cosine without sine. So this here is a secant of the fourth x minus 2 secant squared x plus 1. And then we would multiply by secant cubed. So I'd end up with an integral of secant to the 7th x minus 2 secant to the 5th x plus secant cubed x to x. So the core issue that we have to do, the core issue is odd powers of secant. These are the two cases that did not fit into our substitution. Even powers of cosine and odd powers of secant. Those are the ones that are left over. Those are the ones that we're going to have to learn how to integrate. Any questions? All right. So we know that we can't use substitution if we have even powers of cosine, and we can't use substitution if we have odd powers of secant. We go back to our original plan. To make the substitutions go, we need to be able to save something for dw. And in these cases, even powers of cosine and odd powers of secant, we won't have what we need for the dw to make the substitution work. So now we have to do something else. What is one of the something else that we can do? We've got integration by substitution. It's off the table for these two. What's the other thing that we have? So all we have left is parts. So parts is possibly something that we can do. However, we're going to need more pieces to make parts go. Remember that in parts, dv needs to be something that we can integrate. And also remember, we don't want to make things worse. The other thing that we can do, well, actually, let me change up the plan a little bit. So parts, let's talk about parts. We can integrate this cosine squared using parts, but we have to be clever about how we go about it. So, and this involves an actual useful trick for later on. So let's integrate cosine squared by parts. Because it's the only other technique that we have right now other than doing something sneaky. So after this, we're going to have to learn how to do something sneaky. We're going to have to get all MacGyver on this. Well, I think I'm on page 3. There we go. So let's integrate cosine squared x to x by parts. Going forward, after we integrate a cosine squared by parts, we are not going to integrate cosine squared by parts anymore. In general, we're not going to integrate even powers of cosine by parts. But integrating cosine squared by parts gets us some other stuff that's going to be useful moving forward. So we're not doing this because this is the way. We're doing this because it's useful to see. That's an important thing to think about. Not because this is the way. It's just going to work for us for now, and we'll get some stuff out of it. So we're going to integrate cosine squared x to x by parts. That means we need to assign a u and a dv. Then we're going to calculate the du. And then we'll calculate v. And then we'll put things together in the parts formula. We have a few options that we can try. I can put cosine squared in the u column and dx in the dv column. So I can either do this, cosines, I could put all the cosines here and then just make dv the dx that's left over. So that's one option. If this is the case, then I didn't plan very well for my du, because my du now is going to look like 2 cosine x times minus sine x. Dx. And v is just going to be x. And all of a sudden, I'm not really a fan of this, because now what I'm going to have to integrate is an x cosine x sine x. So right now I'm looking at this and I call ew. Not liking this. What it would look like, let's press on though. What it would look like is we'd write the integral of cosine squared x to x. I'd have u times v. So I'd have x times cosine squared x. So there's my uv. Minus the problem is going to be this one, the integral of v times du. I'm going to factor out a -2. And what I have left is x times cosine x sine x. If it was just the cosine x sine x, everything would be fine. I can do a substitution. W equals cosine and dw is negative sine, everything would be fine. But that x is really messing things up. If we just ignore that it's there, then we could proceed with substitution and try to get partial credit. Don't laugh. I've seen students do that. I've seen students literally just erase the x and say, oh, I didn't see that. And then hope for partial credit. So this plan failed. I don't like this plan. I don't want to proceed with this. So let's try something else. So plan B, I need to pick a u and a dv. I can't just put 1 for u and dv as cosine squared x, because if I knew this, I wouldn't be using parts. I would just write down my answer. Oops. So this is breaking Leach's first rule of integration by parts. dv has to be something that you can integrate. So if we could integrate cosine squared, we wouldn't be doing parts. We would just be writing down our answer. So plan C, the last thing that we have, I put 2 factors in u and none in dv. I tried putting no factors in u and 2 factors in dv, so I have one thing left to do. I'm going to put a half a power in u and 3. That's crazy. I'm not going to do that. I'm going to split it 1 and 1. So we're going to split the u and the dv. So if u is cosine x, then du is minus sine x dx. And v, the derivative of cosine, the integral of cosine is sine x. So this looks like something that we can work with. So the integral of cosine squared is uv. So I have cosine x sine x minus the integral of v times du. So I'm going to factor the negative out. And sine times sine is going to be a sine squared dx. Any questions? We finally landed on some parts that we can actually do, or that didn't make things worse. That's what plan A happened. What happened in plan A? Plan A, we made things worse. We started combining trig functions with polynomials. That made things worse. In plan B, we broke the other rule of parts. dv has to be something we can integrate. We wouldn't be doing parts if we knew what the integral of cosine squared was. So plan C, we split the cosines. So at least we've made progress. Cosine times sine plus the integral of sine squared dx. Now at this point, you might be thinking, we'll do the same thing. Integrating sine squared, I'll do the same thing I did before, or to get here. I'll split the sines. Let's try that so that we'll see that it doesn't work, and then we'll have to come up with a new plan. Splitting the sines isn't going to work either. Observe. So let's say, well, I've got sine squared. I'm just going to do the same thing. I'm going to say that u is sine x and dv is sine x. If u is sine x, then du is cosine x. And so far, we're not seeing a problem. Everything seems cool. V is going to be cosine x. Oops. So my integral is going to be sine times cosine minus the integral of cosine squared. So what I end up with is this cosine x sine x is the same. I'm going to have this one that just follows down. So I have cosine x sine x plus, and then my integral, which will be integration by parts, is going to be sine x times cosine x minus the integral of cosine times cosine. Let's see, I'll follow the same pattern I did before. So cosine squared dx. Any questions so far? So now we see a problem. Because now we got an integral of cosine squared. Now I see a problem. I made a mistake somewhere. I'm glad this mistake got recorded. Can anyone see where I dropped a sign somewhere? So we have still run into a problem, but it is not the problem that I know is supposed to happen. So we're just going to have to hold off on this. This will be a lesson for me for not rewriting my plans on the fly on a Monday. All right, someone find out, take a look at this and figure out where I dropped a sign somewhere, a positive or negative.
Professor, was it with du, negative sine x dx?
The derivative of cosine is negative sine.
Right, when you brought it down to the next line, there's no negative.
Right, but it's uv minus the integral of v times du. So I multiply v times du and it's negative, and then I factor the negative out. Derivative of sine is cosine. What's the integral of sine?
Negative cosine?
Negative cosine.
You already put negative, right?
I didn't put negative for this cosine. The integral of cosine is
Oh yeah.
negative. The integral of sine is negative cosine.
Okay.
There we go. So what does that make? That makes a negative cosine, and that makes a positive cosine squared. All right, now, I did the same thing. Sign errors, they'll get you every time. So now we can see a problem, because notice that we have cosine sine plus a negative cosine times sine. So what happens to these two terms? Now I've fixed this sine problem. Found it. So what happens is these two terms now cancel out, and we're left with the integral of cosine squared x dx is equal to the integral of cosine squared x dx. And that is not helpful. It's just that the one on the right is more colorful than the one that we started with. So we have gotten nowhere. We've gone back to the beginning. This is because splitting the signs isn't going to work. The problem was splitting the signs. Splitting the signs didn't work because it just cycled us back to where we started. Man, if I hadn't dropped that sign, I'd be able to reveal to you the secrets of this particular problem and how we can continue our integration without splitting the signs. And gosh, if I was able to get to that today, then all secrets of integration would have been revealed to you. And it would have been like I plugged you into the matrix and just dropped all this integration into you. But unfortunately, since there's going to be between today and tomorrow, we're not going to be able to figure out what to do with this sine squared until tomorrow. We're going to have to work for all of our integration knowledge moving forward. It would have been so simple if we could have just, you know, if I only had not dropped that sign, everything would have been fine. But now it looks like we're going to have to work for it. Anyway, apart from that, I believe that it's apart from that, I believe that that's it. I'm done. Email this to your grandma and I'll see you some other time.